There's many implementations of cellular automata, from 3D blocks to 2D grids or one-dimensional arrays. One of the most well-known is probably Conway's Game of Life. The rules are simple. You have a grid and each cell is either alive or dead. One generation is when the rules are applied to each cell, and there's 4 rules which determine what each cell does, which can be condensed into the following behavior. Cells with 2 or 3 neighbors survive. Dead cells with 3 living neighbors become alive, and all other cells die in the next generation. It kind of helps if you've ever played Minesweeper. It's slightly counterintuitive to think that simple rules can produce complexity, but Cellular Automata help to show you just how much complexity can arise from simple rules. I could spend 10 minutes alone, which is a lot considering I'm Gen Z, watching these living organisms move, replicate, inevitably die off, or watch as the system approaches maximum entropy. There's a lot of different patterns in Conway's Game of Life, similar to different strains of bacteria and viruses. There's what are called gliders, puffers, and breeders. Not to forget spaceships. And guns. There's even guns, oh my gosh. What may be more fascinating is that you can simulate the entire game of life in the game of life. Well, enough about Conway's Game of Life. There's also many other forms of cellular automata, some of which are in a grid similar to Conway's Game of Life, and there's some pretty interesting ones out there, like some swirly ones and some fiery ones. Spicy. But moving into the single dimension is where some of the more interesting rules come into play. With one-dimensional cellular automata, the rules don't seem as behavioral, like with Conway's Game of Life, but instead can seem more nonsensical, simply as specifying each input pattern with an output state. Even though these are one-dimensional, they're still technically 2 dimensions because the vertical axis is time. Okay, small tangent, but it's interesting to note that some of these cellular automata rules appear in nature. For example, there's a few seashells out there which have patterns very similar to a few cellular automata rules. This one bears the common name Zigzag Venus, which there are a few pictures that better illustrate the pattern, but this is what I could find that has the proper licensing to show you. Regardless, you can clearly make out a pattern of triangles beginning to form, similar to Rule 90. There's also another shell which has a way more definable pattern. It's called the textile cone or the cloth of gold cone. And while I mean, just look at it. It's actually kind of amazing the resemblance it has towards the Rule 30, or the resemblance Rule 30 has to the cone. There's also a chemical reaction called the Belousov-Zhabotinsky reaction, which can also be modeled with cellular automata. Funnily enough, there's another sea creature called the giant pufferfish whose skin resembles a Belousov-Zhabotinsky pattern. Kind of interesting, eh? Anyway, back to the rules. A few rules of interest are Rule 30 and Rule 110. Starting with Rule 30, it's interesting because it illustrates computational irreducibility. This flies in the face of typical science and physics perspectives and shows that even when you know all the rules of the system, you can't accurately predict what the system is going to do. In better words, if I were to throw a ball through the air, if you knew the initial conditions of the ball, you could easily predict or plot the trajectory of the ball. But with Rule 30, that isn't the case. You have to go through every single step along the way. If we were to use the ball analogy again, or better yet, another cellular automata rule, Rule 110, and pretend that these patterns are balls flying through space, if we pause the simulation, you can accurately predict where the ball is going to end up in the next 30 iterations. You don't really need to calculate all this in-between stuff, you just know it's going to end up here. This is an example of computational reducibility. Computational irreducibility is the opposite of this, where you have to compute everything in between. If we understand a system, we can usually predict what it will do, but that's only because we live in a pocket of reducibility. With fancy instruments, we can now peek into different pockets or layers of reality, like at the very small scale in the realm of quantum mechanics. At that level, it's fundamentally different, where things are non-deterministic or unpredictable. Even though we may know the rules of the system, we can no longer jump ahead and predict what it's going to do. We cannot outcompute the universe, and Rule 30 is just a nice way of illustrating that. It's very counterintuitive because it's very easy to see a ball moving and be able to predict where the ball is going, But we're not talking about balls here, we're talking about this. It seems as though every cell leading up to it are all necessary and need to be computed fully. It brings up a question though. Is this irreducibility a problem of our own making? In a computer simulation, there are very clear and definable moments in which the state changes from one to the next. In the real world though, time is smooth or a sort of continual iteration, so maybe in reality this wouldn't matter? This whole idea of single moments in time or time being smooth is a whole thing in and of itself. Search up Zeno's arrow for more information about that. Back to Cellular Automata, if you recall, there was also a rule called 110, which we used for that ball example, but we're not done with rule 110 yet. It's also a good place to start where Cellular Automata, or these basic principles we've gone through so far, can be used to construct a potential theory of everything. Similar to Conway's game of life, where space is defined as a grid of cells, in Wolfram's physics project theory, space in our universe are made with atoms of space, and they relate to each other in a hypergraph. Here's where Rule 110 comes into play. If you take a look at it, what does it look like to you? I hope you guessed that right, because I'm going to say, that's right. They're similar to particles moving through space and interacting with each other. So if we apply the same idea to a 3D version and throw in a fancy word like hypergraph, that's basically what this whole idea is. What's interesting about this idea or model is that it provides a sort of groundwork that other theories can work on top of. Like it turns out, with this theory, you also end up with relativity. I find this is a nice way to comprehend time dilation. This graph illustrates how the speed of light is a constant. Because space and time are the same thing, the faster you move through space, the slower you move through time. It's either more through space or more through time, which is why the speed of light is a constant. You always remain somewhere here on the graph. In the cellular automata theory, space and time are discrete. However, every cell has a certain amount of computation. This computation is basically the speed of light constant. Because everything has to go somewhere, it will either use this computation to recreate itself in another atom of space, or it will remain still and spend its computation traveling through time, or taking its clock, so to speak. And so if a cell is traveling through space, it isn't traveling through time. Different cells can be moving through space at different rates, and so you end up with relativity as well. There's a lot more to unpack with Wolfram's physics project, and it seems to get brain melting fast. So what started as a video wanting to talk about, pretty patterns, quickly turned into talking about a theory of everything, which is not something I've researched enough to talk about right now. So this is probably a good place to stop. Love you guys. Bye-bye.